This is a video on math, democracy, and voting, its flaws and paradoxes. My name is Christopher Scott Vaughn. I'm an assistant professor of mathematics at Montgomery County Community College. I'll begin with just the connections between math and democracy. Math and democracy, in many respects, essentially were born at the same time and place in ancient Greece, around 500 BC, around the time of the discovery of the Pythagorean theorem and the principles of mathematics as a deductive science. Mathematical discovery suggests there are these objective truths to be found, that anyone, regardless of political position, could find these truths through the use of reason. Thus people could decide for themselves what is truth, and thus govern themselves. The ideal of democracy is that individuals have a say in the course of their lives. To improve one's life and to improve society, individuals must make good choices, and this requires knowledge. If people are voting on issues in a democracy, the ideal is that people understand those issues. The ideal of a democracy implies the search for truth, and thus leads back to mathematics. Let's look at how groups decide in a process of voting. When there's voting for 3 or more candidates, we don't really use majority rules. Typically what we're really using is plurality to determine the winner. For example, consider an election with 3 candidates, A, B, and C. Suppose that A gets 40% of the vote and B and C each get 30%. In this case, there is no candidate with a majority of votes, and there would be no winner if you were looking at majority rules. Majority rules means that you'd have somebody with more than half, with over 50%. But what we're really doing here is, if you're just saying that A is the winner, you're saying that's because of a plurality. Using the plurality method, A has more votes than any other candidate, and therefore, specifically by the plurality method, A is the winner because A has more votes, but not a majority. So plurality is a method of voting that determines the winner based on whichever candidate has the most votes, specifically the most first place votes. Having the most votes doesn't mean that that candidate has a majority. This example here illustrates if you have a total of 11 votes and A had 5 votes, B has 4 votes, C has 2, that's 11 total, and A has more than anybody else, but if you're looking at half of 11, that's technically 5.5, so you'd actually have to have 6 votes to have a majority. So in this example, A has the most votes, but it's not a majority. Candidate A has 5 votes, but that's still less than half of the total votes. A would win by the plurality method. Clearly a majority of the voters, which would be 6, have split between candidates B and C. So a majority is actually choosing someone else besides A, right? So A wins by plurality by having more votes than any other, but in this case it was the majority, the 6, that actually split between candidates B and C. So if we're counting who has the most votes, then we are really doing what's called counting by plurality. We're looking for the plurality winner. The winner with the candidate with the most votes is the candidate that wins by plurality. Okay, so now that I've established what exactly I mean by plurality voting, I'm going to go through and really just show the fundamental flaws with this particular method of voting. Here's an example with 100 voters. You've got these voters organized into 3 columns here. There's 40 people that put Trump as their first choice and Rubio as their second choice, Kasich as their third, Cruz as their 4th choice. So we have 4 candidates, right? We have 35 people that have Cruz as their first choice and Kasich in second, Rubio in third, Trump in 4th. And then we've got the column at the end on the right, 25 voters there, and their choices ranked from their first choice, second, third, and 4th. Now looking at this table, the winner by plurality would be Trump. He has more votes in first place, and when you're voting by plurality, all that matters is your first choice. That's all you can do, is vote for one person for a particular office or in an election. When it's plurality, it only matters who your first choice is. You can only vote for that one candidate, your first choice. So Trump would win by 40 votes, more than anybody else. Cruz gets 35 votes, Kasich gets 25, Trump would be the winner. But 60% of the voters put Trump as their last choice. Yet Trump is the winner by the plurality method, a fundamental flaw in this method of voting. Right? Trump has more votes than any other candidate, and he wins by plurality. However, a majority, more than half of the voters, put Trump as their last choice. Further flaw with plurality voting is that, in fact, when we are comparing candidates one-on-one, Kasich beats every other candidate and yet does not win by the plurality method. Kasich is beating Trump here 60-40. And he's beating Cruz 65-35. And he also beats Rubio 60-40. If you go through this group, how would they vote if you had only two candidates? Kasich picks up a majority when he is compared one-on-one with all of the other candidates. This is what makes Kasich called the Condorcet winner, or a Condorcet candidate. He's not the actual winner if we use plurality, but he's the Condorcet winner. He does beat every other candidate by a majority when compared one-on-one, but he doesn't actually win if you use plurality. And also, I have to say that you can't actually use the Condorcet winner criterion as a method of voting, because you don't always have a candidate that beats everybody else one-on-one. Otherwise, we could use that as a method of voting. So, flaws with the plurality method, 2 highlighted so far. We have seen the plurality method of voting has some fundamental theoretical or mathematical flaws. It is possible that a majority of the voters consider the winner of the election to be their last choice. And even if there is a candidate that wins one-on-one comparisons with every other candidate, that candidate might not actually win the election if the plurality method is used. So we step back here and think, all right, is there any other way of voting besides plurality? What about majority? Well, that really only is a method of voting when you've got two candidates, because in the case that you have two candidates, technically, if you had an even number of voters, it could split. You wouldn't have necessarily, theoretically, always somebody with a majority. But this is unlikely if you have a lot of voters. So if we sort of discount that possibility, voting with two candidates, you can look for the majority, the candidate with a majority, and that is a method of voting that will satisfy all sorts of different conditions of fairness that we will look at as this video progresses. Majority rules will satisfy all of those, but we don't use majority rules when we are voting with three candidates, because there may be nobody with a majority. So then, voting methods when there are three or more candidates, it turns out none of them will satisfy a basic set of fairness criteria, which is known as Arrow's impossibility theorem. This is something that was discovered and proved in the 1950s. Fundamental result of the mathematics of voting. And as an example of some other methods, some methods of voting, I have already listed plurality, but then there's this Borda count method, instant runoff method, sequential pairwise, and there are other methods that I won't go through here for determining a winner when there are three candidates or more. But it turns out that none of the ones listed here, and none other that have been discovered, and it has been proven that there will never be a method of voting for three candidates or more that will always satisfy a basic set of fairness criteria. I won't go through all of them here. I do list those fairness criteria at one point in this slide, but I don't go through every one of those conditions and how each of these methods fail them, but you will see those conditions listed. And on top of the fact that each of these methods has its flaws, another distressing mathematical conclusion here is that different methods actually produce different winners with the same voters. And this is the next thing that I'll go through here. The following examples will use the same four candidates. I'll just name them A, B, C, and D. And we'll use the same 9 voters in these examples that follow, with those voters with the same preferences. So the voters and their preferences don't change. I'm going to change the different voting methods, and you'll see that we come up with a different winner based on the method that we use. So we could ask, Is it the voters that are really choosing the winner, or was it the method of voting that's actually choosing the winner? So each method has its own fundamental flaw, and different methods produce different winners. It's a sort of distressing discovery, but I hope to put some sort of positive perspective on that as we go through and at the end. This is the table that I will use in the next 4 examples of voting, and I'm going to demonstrate my different methods of voting in these examples with these same 9 voters and their preferences. So we have 4 candidates, A, B, C, and D, and they are listed in this table according to their preferences of those voters. Of those candidates. So let's go back to plurality again. With the plurality method, all we're doing is looking at the voter's first choice. A voter can only vote for his or her first choice, and so that's all that matters here. And you can see that A gets 4 votes for first place, B gets 2, C gets 2, and D gets 1 in this case. So A would be the winner. Borda count is another method of voting that we actually take into account the ranking of each of the voters and where they put those candidates. So you can see that I had 3 voters that ranked A first, and so what that does is it gives A 9 points. In the way that I'm using this method here, I'll say that you get 3 points if you're ranked first, and 2 points if you're ranked second, 1 point if you're ranked third, and you get no points if you're ranked fourth. Now, some people will do it 4 points here, 3, 2, and 1, and you'll end up with the same answer because what we're really looking for is whoever had the most points, and it'll just scaled differently. So looking through and tallying up the points, A gets 13 points here, and that's partly because A, while ranked by these 4 people first, A is ranked very low at last choice or next to last by everybody else. And so A did well among a few people, but is ranked really, really low by many others, and so doesn't actually win. B is ranked only by 2 people as first, but he picked up a lot of second and third place votes, and so B actually wins by this Borda count method. B has the most total points, so B is the winner by the Borda count method. Instant runoff is another method looking again at the same table with the same voters. What I do is in instant runoff, I would look for, is there any candidate that has a majority right off at the very beginning, has a majority of first place votes. Now that we've got 9 people voting, half of that would be 4.5. If there's anybody with 5 first place votes, they'd have a majority. But there is no candidate with a majority. So then this first step, or I guess the next step after that in instant runoff, is to see if there's which candidate has the fewest number of first place votes. And if there was a tie for fewest, we would cross them both out. And so in this case, D has only 1 first place vote. So in this method of voting, I'm going to cross out D. And I'm going to cross out D in every instance because D is getting removed as a candidate. So once D is crossed out and removed, what I'll do is I'll assume that each one of these voters are keeping their same preferences that they had before. Like, let's say these 3 people here on the first column, if they liked A first and B third and C fourth, and now D is gone, they'll still like B better than C. And this is the case with everybody. So all of these open spaces, the ones that are ranked lower than the open space, they're going to just all move up like that. Now we can see, is there a candidate that has a majority? And if there was, that would be the winner. Otherwise, we continue removing candidates. So we have still nobody with a majority. And at this point, B has the fewest number of first place votes. So B is going to get crossed out next. You see that by reorganizing the table, I can see that there were actually 2 people. If I go back, there's 2 people there that rank B first, then C, then A, right here in the middle. And it's those 2 people that create 1 column on the next screen. There are 3 people that all have the same preferences, CBA, and these 4 are all with the same preferences. So that goes into this new table, and then we ask, is there anybody with a majority? And the answer is still nobody with a majority, and therefore we're going to remove the candidate with the fewest number of first place votes, which is B. So B has only 2 first place votes, so I'll take B out, remove B, and then assume that all the voters' preferences still remain the same with respect to the ones that remain. So it looks like that. We had 4 people who put A first and then C, but we actually had 5 people that like C over A, and that's a majority. C now has a majority of first place votes. C also has a plurality of the 2. So C is actually going to be the winner by using instant runoff. One last method of voting to look at here, and that is the sequential pairwise method. When I do the sequential pairwise, I have to look for a particular order in which the candidates are compared, and then they're compared sequentially through that order. So that order of candidates is called the agenda. So in this example, we've got an agenda listed up here, A, B, C, and then D. That is part of the sequential pairwise. You have to decide what sequence you'll go through the list. In fact, even that could change the outcome in this particular method, how you rank or how you organize, how you list the candidates. And those candidates now are going to be compared one-on-one for a majority. When you compare one-on-one, that's only 2 candidates, you can get a majority in each of those cases. And so the majority winner in each contest then moves on to face the next candidate in the list. And so in this particular example, we're going to start with comparing A and B. So if I compare A and B, I've got B beats A by 5-4. You can see how I've kind of highlighted which of the voters ranked B higher than A, and therefore prefer B over A. And in a total of 9 voters, B is winning with a majority against A, 5-4. Close, but majority. So B is the winner in that first contest between A and B. So that winner of that contest moves on to face the next candidate, C. So we've got B and C, and if we compare B and C, B is winning in these particular columns. You've got 6 voters here, right? 3 in the first column plus 3 more, where B is ranked higher than C. So if it was just B versus C, B wins in that contest. So then finally B is moving on to the last candidate, which is D. So in that final contest between B and D, comparing just B and D, D is actually preferred 5-4, again a majority. So D would actually be the winner if we had gone through a sequential pairwise method of voting with this particular group. So, is this at all disconcerting? Different voting methods were producing different results. Candidate A was winning with a plurality. Candidate B won using Borda count. C won when I went through the same group with instant runoff voting. And candidate D won if we use sequential pairwise. And that's specifically with that agenda. It could have been a different outcome even with a different agenda, even in that particular method. So which of these is really the best, and how can we decide? Ultimately, there is really no best method in any absolute sense. It's Arrow's impossibility theorem from 1950 that shows that it's impossible to create a method of voting for 3 candidates or more that doesn't have some kind of fundamental theoretical flaw anyway. Beside the fact that the different methods produce different winners, each of them has theoretically the potential to violate basic principles of fairness. And that's not just of a condition of the voting methods that we have so far, that we've looked at so far, or that we know so far. It's fundamental to voting in any group with 3 candidates or more, that no matter what method you created, there would always be the theoretical possibility of a fundamental flaw in a violation of some basic conditions of fairness that I'll demonstrate more of. Kenneth Arrow won a Nobel Prize for this mathematical result in 1972. I'll go through here just listing where these different methods are used. Plurality is used, of course, in most political elections in the United States for local, state, national elections. Borda count is used by Major League Baseball to determine the league most valuable player. And it's also used to rank NCAA football teams in the AP and the UPI polls and to determine the Heisman Trophy. The instant runoff method is used to elect presidents in Ireland and in India. It's also used to determine the host location of the Olympics and the winners of the Oscars. And it's been used for some elections for political office in Maine and California and Minnesota. Sequential pairwise is essentially the process of voting on legislation that's done in the United States Congress. I listed approval voting here, but I didn't go through that one. I decided to take it out of the video just to save time, but it's another method that itself has its own flaws. It's used to elect the Secretary General for the United Nations and some other associations. All right, we'll start here with a summary of the different voting method criteria that you could use to check for the fairness of a method of voting with 3 candidates or more. The first condition listed is this majority criterion. That is, if there's a candidate that has a majority, if a candidate has a majority of first place votes, then that candidate should be the winner of the election. That seems to be fair to the voters and the candidate, right? If you have a majority of first place votes, you should be the winner. And we'll see that there are certain methods, for example, Borda count, where that's not necessarily going to happen. And therefore, Borda count will say fails that condition or that criterion. Second criterion on the list, the Condorcet winner criterion. If there's a candidate that beats every other candidate in one-on-one comparisons, then that candidate should be the winner of the election. And you've already seen with plurality that that isn't necessarily going to happen. And therefore, we could say, theoretically speaking, that it is possible that with plurality, the Condorcet winner or Condorcet candidate isn't elected, and therefore it's a possibility that the plurality method fails the Condorcet winner criterion. Independence of irrelevant alternatives criterion. This condition says that if a second vote is held and a non-winning candidate had dropped out, then the previous winner should still win the election. We'll see that plurality fails this one as well. The Pareto criterion. If there is some candidate, A, that everyone prefers to another candidate, B, then B should not be the winner of the election. Another condition of fairness that would be fair to A. If everyone prefers A over B, then how could B win? We'll see that some of the methods of voting with 3 candidates can violate that condition of fairness. And finally, the monotonicity criterion. That states that if, after a second vote, the only changes in voter preferences are in favor of a certain candidate, that candidate should not lose. So these criterion are measures of fairness of a voting method. Every method ever created or that ever will be created will fail at least one of these criteria. This is Arrow's impossibility theorem. For example, Borda count fails the majority criterion, and it also fails the independence of irrelevant alternatives criterion. Instant runoff voting fails the independence of irrelevant alternatives and monotonicity, and plurality fails the Condorcet winner criterion and the independence of irrelevant alternatives criterion. Looking at a table of a few different common methods of voting and these particular criterion, it was approval voting that failed that Pareto criterion. So does sequential pairwise. Sequential pairwise also fails the Pareto criterion, for example. I'm going to highlight a few of these examples in some examples after this. Let's take a look at Borda count and a flaw or problem with Borda count. Here we have 11 voters and 4 candidates, and by Borda count, who would win this election? So we'll look at the point totals for each candidate. Each candidate receives points based on how they are ranked by the voters. And if I use first place is 3 points and second place is 2, third place you get 1 point, and ranked fourth you get 0 points. Here's a candidate, A, who has more than half the votes for first place, a majority, and yet you've got 5 people that ranked A last. And so A could feel justified in saying, I should win this because I have a majority of first place votes. But A won't actually be the winner by the Borda count method. If we tally up the points, B has 21 points here, A only has 18. It's because you've got 5 people that ranked A last. So to try to correct the problem of having a candidate that a large percentage rank low and maybe some other candidate that's sort of a middle ground that some people like a lot and others like okay, this Borda count is a reasonable approach to deciding a winner, but it fails a fundamental condition of fairness that we had a candidate with a majority of first place votes that doesn't actually win. A had more than half the first place votes, wouldn't actually win here. The winner is B with Borda count. So this example is showing that Borda count can violate the majority criterion. For another example, I want to talk about straw elections. A straw election is really is the same thing as a survey. It's like a trial election or a sample election or just the survey before the actual election. And the straw election is essentially asking who would you vote for right now. We consider straw elections here because some of the flaws in voting are apparent when you consider the voters' responses in the straw election and then the actual election. So the monotonicity criterion holds that if there's an election held after the straw election or the survey, and the only change that is made is for some voter to move the previously winning candidate higher on their preference list, that candidate should still win the election. And it's the instant runoff method of voting that doesn't satisfy this monotonicity criterion. Theoretical example here that I'm going to show how it could happen that instant runoff would fail this condition. So voting by instant runoff here, Bloomberg and Sanders are tied with the least first place votes, and they would be eliminated because we've got 13 voters, half of that 6.5. Nobody has a majority. Clinton's at 5 votes. It's almost, but it's not a majority. So with no majority, you look for the candidate with the fewest number of first place votes, and actually it's tied in this case. Sanders and Bloomberg both have 4. They're tied. So they're eliminated, and that leaves only one candidate remaining. Clinton would be the winner in this survey with these voters with these preferences. Clinton is currently the winner. Now suppose that one candidate on the far right here decides to move Clinton to their first choice in the actual election. So here was the survey, and here is the actual election. And the only change that I've made is I've thought, well, what if that one person there decides to rank Clinton first? Now remember, in the survey, Clinton won. In the actual election, with that one person making one change that's favorable to Clinton, it seems it would be fair to Clinton that she would still be winning, but with instant runoff, the outcome is going to be different. You see, you've got Clinton with 6 votes, which is not yet a majority, and so we have to look for the candidate with the fewest number of first place votes, and that's Bloomberg here. Bloomberg, if we're looking at the actual election and the candidate with the fewest number of first place votes, Bloomberg here has the fewest number of first place votes with only 3, and so Bloomberg is going to be eliminated. So if we eliminate Bloomberg, and if he's no longer included, and we look at everybody's preferences without Bloomberg, for example, these first 5 people in this column ranked Clinton over Sanders, so I'm going to assume here that they still rank Clinton over Sanders, and these 4 people ranked Sanders over Clinton, and so did these 3. So if those preferences remain the same, with only 2 candidates, the preferences can be reorganized in this way, and now you see what's going to happen. You've got 7 people who would vote for Sanders first, and according to the method of the instant runoff, which is named that way because this is all done after the voters have placed their preferences, Sanders is going to be the winner now. Sanders has 7, a majority. Clinton has 6. Sanders wins. Using the instant runoff method, the preferences are recorded. Using the instant runoff method, preferences as recorded in the election remain. Right? Now the winner is Sanders. Sanders has more votes. The fact that this is the logical consequence of a change that was favorable to Clinton seems paradoxical. Right? Clinton was winning in the survey. And the only change in the actual election is one voter who changed their preference to rank Clinton, who was the winner, higher, a change that should be favorable to Clinton. But as a result, Sanders is the winner. So that's demonstrating that instant runoff can theoretically fail to satisfy the monotonicity criterion. Let's look at plurality and how it fails the independence of irrelevant alternatives criterion. That was, if a second vote is held and a non-winning candidate drops out, then the previous winner should still win. This condition does not always hold with plurality voting, as you will see in the next example. We've got 15 people here, no majority. We've got, with plurality, that is not even a requirement. Trump has more votes than anybody else if the election were held with this table as it is here. Suppose that Rubio now drops out and all the preferences remain, and that would be what's listed in this table here, and you can see the outcome with Rubio removed. Now Cruz has 8, which is more than Trump, and it's actually a majority, and Cruz actually wins plurality. When you remove a candidate that was not even winning, it changes the outcome, which isn't all that surprising in and of itself, but realize that we didn't change any of the voters' preferences. It wasn't like there were more voters that showed up for Cruz. It's the same voters with the same preferences. The only change was to remove a candidate that was not winning initially, and the outcome is to change who the winner is. I'll move on now to talk about a fundamental flaw in voting when there are 3 candidates, and this is the voting paradox of Condorcet. So Marie-Jean-Antoine Nicolas de Caritat was the name of a French philosopher, mathematician, and political scientist who was born in 1743. And he was given this title, Marquis de Condorcet, a title of nobility, meaning he was part of the aristocracy in France in a period right before the French Revolution. The French Revolution began when he was 46, and in spite of his position in the aristocracy, he advocated equality among men and women and people of all races, and he believed in a constitutional form of government and a rule of law instead of monarchy and aristocracy. And he was arrested for those beliefs. He eventually died at the age of 51 because of those beliefs, and the circumstances of his death are unknown, uncertain. One of the contributions that he made is the discovery of this paradox that we now call the voting paradox of Condorcet. He made many contributions both to math and political science, and the voting paradox of Condorcet is described with the concept of transitivity. In algebra, transitivity is a simple idea. An example occurs with the greater than inequality. If we say that A is greater than B and B is greater than C, then A is greater than C. And in voting, we refer to the transitivity of the voter preferences. If a certain voter prefers candidate A more than B and prefers B more than C, then one could reasonably assume that this particular voter would prefer A over C. So the voting paradox of Condorcet is the following. It is, even if we assume that the preferences of the individual voters are transitive, this doesn't imply that the preferences of the group are transitive. So the following is a real example of Condorcet's paradox. It was in the Education Act of 1956. In 1956, the breakdown of the 435 members of the House of Representatives was 232 Democrats and 203 Republicans. However, at this time there was a significant difference between the 116 Northern Democrats and the 116 Southern Democrats. That 232 total Democrats was split into two very different groups on some major issues. And there was a vote to be held regarding federal funding for schools throughout the entire nation. It was an amendment called the Powell Amendment to that legislation that was offered that would provide funding only to districts that favored integration of blacks and whites in the schools. And the Republicans were against the legislation from the beginning, but they preferred promoting integration over the unconditional funding. And the Northern Democrats liked the idea of supporting the integration through the funding, but they still wanted to provide the funding. And the Southern Democrats wanted the school funding, but were completely against the federal interference in the local control over the integration of the schools. And so there were kind of three different sort of voting blocks or different coalitions of preferences here. The Republicans, with 203 voters, would have ranked no bill as their first choice, amendment as their second, and the original as their third choice, while the Northern Democrats put the amendment as their first choice. Their second choice was the original bill, and the last choice for them would have been no bill at all, whereas the Southern Democrats saw the original bill as their first choice, and then no bill as their second choice, and the amendment for them was the third and last choice for the Southern Democrats. Now, we're going to assume preferences of the voters in each of these groups are transitive. For example, the Republicans, if they ranked no bill over amendment and amendment over original, they would rank certainly no bill over original. And that's the case with each of these groups. I'll assume transitivity of each group. The Northern Democrats, if they rank amendment over original and original over nothing, then they will rank amendment over no bill. Now, assume the transitivity of each of these individual voters in Congress, and therefore each of these three different groups transitive in their ranking of the preferences. But then when you look at the entire outcome of the group, you will see that the preferences of the group are not transitive. Let's compare just the amendment with the original bill in this group of voters. The amendment wins 319 to 116, and that's because the Republicans and the Northern Democrats have teamed up, and both of them prefer the amendment over the original, and that makes 319 to 116, the 116 for the Southern Democrats. Let's compare just no bill versus the original. If it's just a contest between the original and no bill, now the original would win because the Northern and Southern Democrats team up, and that's 232 to 203. Original wins if it's a contest between just those two, and it's a majority in each of these cases. That's the winner, wins by majority. Now let's compare just the amendment versus no bill. If you're comparing those two choices, no bill actually wins because the Republicans and the Southern Democrats will team up and form a coalition, Republican and Southern Democrat, and no bill wins. 203 plus 116 from the Southern Democrats makes 319 to the 116 from the Northern Democrats. So then we have no bill is the winner in that particular contest. And so looking at the whole entire group, we can now see if it's just a contest between amendment and original bill, amendment is preferred by the group over the original bill. Now the original bill is preferred over no bill by this group. But then if you compare no bill and the amendment, no bill is actually preferred to the amendment by this group. So it creates a situation where no bill seemed to be at the bottom of the preferences of the group, but then the group prefers no bill over the amendment. So it creates a sort of cycle in the preferences of this group. A paradox has occurred. Right? Following a logical process with logical assumptions, we have a result that seems not logical. We've just found that in this group of voters, the amendment is preferred over the original, and the original is preferred over no bill, and yet no bill is preferred over the amendment. So visually, the preferences create this sort of never-ending cycle, where A was the amendment, O was the original, and N represented no bill. So what really happened? The debate on that Education Act in 1956 was during a period of civil unrest in the entire country. At that time, under court order, the University of Alabama had admitted Autherine Lucy, its first African-American student. And the Virginia legislature called for massive resistance to school desegregation and pledges to close schools under desegregation orders. There were 1,000 paratroopers from the 101st Airborne Division and a federalized Arkansas National Guard that protected 9 black students integrating Central High School in Little Rock, Arkansas in 1957. So the real story of this and similar legislation is a complicated story of progress and setbacks. This particular bill, the Education Act of 1956, with the Powell Amendment, the whole bill was defeated, but there were other bills that did ensure progress. In 1956, that Education Act was considered in Congress with the following agenda. First, the original bill versus the amendment, and then the winner of that contest by majority would then move on to face an up or down vote on the bill altogether. So if you just compare the original and the amendment, the result was that the amendment was winning. That's because the Republicans and the Northern Democrats together formed a coalition and voted for the amendment. But then when the amended legislation was then voted on again, whether or not to pass it, to have the amendment or no bill at all, no bill won, and that was because the Republicans then formed a coalition with the Southern Democrats. So that meant no bill was the winner. That is, the bill was rejected and the legislation failed. Powell was a Northern Democrat, but it seems to me like it's almost suspicious that such legislation, an amendment such as the Powell Amendment, could be introduced by the Republicans in the minority because their first choice was no bill, and the outcome is to get their first choice. I don't think that's actually what happened, but I'm sure that's not what happened, but it's an interesting perspective on that particular scenario, how a group in the minority could introduce an amendment that is destined to kill the legislation, which was their first preference. Moving on now to another sort of fundamental flaw in voting, not necessarily the method of voting itself, but the general process of voting in a democracy. It's the concept of gerrymandering. It's this process of redrawing districts to gain political advantage. This is a cartoon that was printed in March 1812, a political cartoon drawn in reaction to a newly drawn district created by the Massachusetts legislature that favored the governor, Elbridge Gerry. This caricature satirizes the bizarre shape as a sort of dragon-like monster. Newspaper editors and others likened the district shape to a salamander also, and used the word gerrymander as a blend of that word and Governor Gerry's last name. This slide illustrates how gerrymandering, which is redrawing districts for political advantage, could actually work. Imagine that you had 50 people here in this first image, and let's say the red boxes represent Republicans and the blue boxes represent Democrats. Now you've got a state here with 50 people, red boxes for Republicans, let's say, blue boxes for the Democrats, and they're, in this particular state, a majority 60% blue, 40% red. So if districting were to occur now to represent these people, let's say with 5 districts and 5 representatives in Congress for this particular state, practical impossibility would have a district drawn in a way that gives exactly 2 districts for the Republicans and 3 districts for the Democrats, and exactly perfectly represents each district. Each congressman represents everybody in their district. Ideal, but impossible. Perfect representation in this first image here. Now there's the term compact that is brought up in this discussion, and compact refers to boundaries that are not convoluted. So these are compact, not convoluted districts, but it's still unfair because if you drew the districts in this way, each district would be electing a Democrat for Congress, and all 5 representatives in Congress would be Democrats, and it wouldn't be a fair representation of this particular state in Congress, and the Democrats would have more power in Congress than is a fair representation of the state. And finally, in this last image, there's another districting that's being drawn out that is not compact because of the convoluted boundaries, and it's not fair as well because of the representation of the state in the districts. You can see that the boundaries now are really hard to follow. These darker black lines are district boundaries. And so this particular district here has a majority Republican. There are more red boxes in this district. So in this district, when it comes to voting for a representative, a Republican, a politician representing the red boxes would win because it has a majority in that district. So it was drawn in a way to sort of capture more red votes, red boxes, and also to break up the majority blue boxes. And so there are actually districts here. This district 1, 2, and 3 that actually will have majority red boxes, majority red voters, and therefore would have representatives that are representing those Republicans. Basically, if the red was the Republicans, then there would be a majority of Republicans in Congress for this particular state, even though there were a minority of people in that state that were actually Republican. Right? There were only 40% Republican, but there are 3 red or Republican districts in the representation in Congress. So not compact and not fair. You can see sort of 2 things being accomplished by this convoluted boundary: is capturing more voters for the candidate that draws them, and also breaking up voters that candidate perhaps wouldn't want, doesn't represent. Breaking up the majority, capturing the minority, building districts that favor the politician that drew the boundary, or favoring the party of the politician that drew those boundaries. For example, Pennsylvania. These are the congressional districts. There are 18 congressional districts for Pennsylvania, and they're different sizes only because some of the areas are more sparsely populated, higher density populations down here in the southeast in Philadelphia. Each district represents roughly the same number of people, but the way in which they are drawn is to capture certain voters that will favor the party that favor the party that drew these boundaries. They were drawn in a way that favors the party by capturing voters that would vote in favor of this particular party, and also to break up areas in which the voters would not favor the party in power who drew the boundaries. So zooming in a little bit, some of the districts that are just so clearly gerrymandered. Here's District 6 for Pennsylvania and District 7 for Pennsylvania. Drawn in a way both to capture particular voters and also have other voters split that might have otherwise been a majority in one district are now minorities in 2 districts or 3 districts. So the real fundamental flaw here is currently in this country how politicians are drawing these districts. It's done about every 10 years after the census. The districts are redrawn, This means that politicians are almost choosing their own votes by designing these favorable districts, and a solution would be to create independent groups, not politicians, or groups that are representing equally both political interests, and have these independent groups redraw district boundaries. So a forward-thinking and positive and hopeful outcome of all of this is to educate yourself. Look on Google and YouTube on the topic first, baby, of gerrymandering, because this is something that we really could solve fundamentally if enough people were interested. But also further look at who your representatives are where you live and see whether they really, truly represent your interests. All right, that's the end of the video. Thank you for watching. I hope it was helpful and interesting.